Sounds like a yes. Good. So what we did in parametric equations, we get our position xy in the plane, but we determine the x position by a third variable time, and we determine the y position by a third variable time. Now I'm not going to get into how to graph all this stuff now, but this winds up being something that looks like this. Okay? But what you can still do is get equations for tangent lines. I want to know the equation of that tangent line at that point. Well, you can still figure out a point, you know what I'm saying? But you'd have to just figure out at a specific time. At time 0, the x position is this, and the y position would be that. If you just plugged in a 0 into that, you know what I'm saying? You would have to plug in to figure out your point time into both equations, but you can still get your point. Does that make sense, Roxana? Well, exactly. So here's the problem, right? So then, I got my point, Mr. Remus, I'm halfway there. How do you get the slope? Well, here's what you can do. I want the dy dx, because you are looking at an xy plane. Okay? You're looking at xy plane. You want the change in y over change in x. But x is in terms of t, and y is in terms of t. Meaning I could take a derivative of y in terms of t. So let's see what happens if I multiply the two. If I take my y derivative in terms of t, and I multiply it by my x derivative in terms of t. Does that help? That's all, it'd be a dy dx over dt squared. That's not helping. But let's try this way. If I said dy dt divided by dx dt. Well, let's see what happens here. Okay, Estella? If I did this, this is the same as dy divided by dt divided by dx dt, going with my old school little symbol there that I like so much. And dividing is the same as multiplying by the reciprocal. So this is dy dt times dt dx. If I multiply these across, technically these would cancel out, even though not really, there's more to it, but if it is a number, and it would leave you with dy dx. So, dy dx is the same as the derivative of the y value in terms of t, and the derivative of the x value in terms of t. So let's do it. I want to know the equation of the tangent line for this relation, not a function, at time 0. Well, what's the first thing you need to do to figure that out? Yep, let's figure out our point. What's the cosine of 0? 1, so what's 5 times 1? Okay, so my x-coordinate's 5, and then what's sine of 0? Y length of the reference triangle of 0 radians. What's that y length? 0 times 2 is 0. You have your point. Okay? Now you need to figure out your slope. So if I did dy dt would be equal to what? The derivative of this in terms of t would be 2 cos t. What's dx dt? Be careful. Yeah, with that negative in front. Okay? So I have my dy dt and I have my dx dt. I couldn't care less about either of those. What I care about is the change in y over change in x, because I want to graph the slope. I need the change in y over change in x. dy dx is equal to this dy dt divided by this, or 2 cos t divided by negative 5 sine t. What is the slope there? Well, let's plug it in. Let's plug in at time 0. What do you get? 2 you get 2 over 0, which is what? Not 0. Undefined. What that point is, on this graph, here's the point 5, 0. There's your tangent line. At that point. It's actually straight up and down. It's got an infinite slope. And this is what you just saw. There's the slope of the tangent line, there's the point. Okay? You have a vertical line at that point. Interesting or no?
Sure.
So this is kind of weird to bring up in this section, but the only reason why they did it is because we're doing this dy, du's, dx's, so they're like, hey, let's also throw parametric back in there. Does that make sense? And that's the only reason why. The majority of the problems tonight are going to be chain rule, breaking these things down. Okay? One last thing, thank you for not packing up 2 minutes early, because that would be weird. So let's open back up and not be rude and disrespectful. Is now we can solve problems like this. Here's my function, x squared over 5x plus 3. Who doesn't like the quotient rule? Sure, why not? I never liked it. What I did to get around it is I treated this as a product rule. Like that. I flipped it up and put a negative exponent on it. Is this the same as that? Sure. Let's take the derivative of it. Overall, this is a product rule problem. So, derivative of the first times the second plus product rule, the first times the derivative of the second. Okay? This is 2x. Again, if you want to flip that down, that's fine. Or you can leave it right there. Plus x squared. And now the derivative of this, exponent, bring the exponent down. Negative 1. 5x plus 3. Negative 2, subtract 1. Times the derivative of what's inside, which is what? 5. Okay? Now some people don't like negative exponents, so they're not going to want to do that. But if you flip everything back down, this is 2x. This is a valid equation. So is this. Multiplying all of this, I get negative